Hiya. So in today's talk or lecture, we're going to finish up week 1 by talking about geometry of Euclidean vector spaces. So remember last time, or in the last video, we gave examples of an inner product, and we said inner products are basically this thing that helps us define angles and distances and blah, blah, blah. And it's like, well, what do you mean? Like, where is this coming from? Like, what? Like, that definition that I gave, like the symmetry, linearity, and positive definiteness, how is this giving us angles and stuff like this? So we're going to see that in this lecture, in this video. So here, note that we are assuming that V is going to be a n-dimensional Euclidean vector space. So we're assuming that throughout the whole thing. So note that from the beginning. So first, how do we define? We're going to talk about length, aka magnitude. How are we going to define this? We're going to let it be this notation. So this is the length or magnitude. And all this is going to be the square root of the inner product. This might seem very weird. Like, what the fudge? Why are we taking the square root of an inner product? And well, let's see this. Let's see why we're kind of doing this. So if we take this formula and we look at length, so we look at our normal Euclidean vector space, like normal Euclidean geometry, where we have the inner product being the dot product. Well, then in that case, we have our length. Well, what is this? This is what I defined it as. But the dot product is, if you remember, this is just, I think sometimes we denoted it as this, right? X dot X. And what is this? This is x1 times x1, so x1 squared, plus xn squared, right? So this is where this idea of length is coming from. It's basically taking the original dot product and extending it to an arbitrary norm, arbitrary inner product. Now this notation, well, like we can't just call it the length. Well, I mean, the value of this is the length, but what is this operation? What are we doing, right? It's not the dot product because it's the square root of the dot product. It's the square root of the inner product. So we need a name of this. And what we're going to call it is we're going to call it the norm, because we're in some sense normalizing the vector to some value. And that normalization is coming to the length. So this is called the norm. And it's a way of defining the distance on a vector space. Length itself is then called the Euclidean norm, since it's the norm associated to Euclidean space. But there's many different ways of actually defining distances on space. So there's different types of norms we can define. We're not going to go too much into these. But just know there are many different ways of defining them. And you can go on Wikipedia and kind of look at different norms and figure things out from there. But for us, we're just going to stick to the normal norm and length and kind of go there. Okay, so we got length. Next up, we also said we're going to talk about angles. So like defining angles and stuff. So what's an angle in this space? So an angle between them, we're going to again use the inner product. And here we're going to explicitly define the angle between two vectors x and y to be the cosine of theta. So here, this is the angle. And what is this going to be equal to? This is the inner product of x and y. But we're going to normalize them. So what we do is we divide by the norm of x, and we divide by the norm of y. And what we're going to say is so here, if you kind of notice, this operation, right, norm, is always going to be positive, right? We're always taking a positive value because we're taking the square root, right? So we're not going to look at this plus or minus. We're kind of always going to consider this as the positive space. And so really the degree or the sign of this is really going to be dependent on this top thing. Only thing with sign. And because of that, we just have to look at the inner product of x and y to see what theta is. So if x and y, if the inner product is greater than 0, then we know that the angle is going to be an acute angle. If it's less than 0, it's going to be an obtuse angle. And if it's 0, then we're going to say that they're orthogonal. At this point, you might be going, well, what? Like, I don't get it, right? Because why would theta, so here theta you're kind of thinking is small versus big. How is this kind of playing into acute and everything? Well, this is really just, again, coming from the original dot product. So the dot product we kind of saw is this is the original dot product, right? So here. So the dot product, another way to kind of see this is it's just x, the norm of x, the length of x times the length of y times cosine of zeta. So it really is coming from the standard definition of it. Now, another thing you kind of notice is I never said which way this angle is going. I didn't say if theta is going clockwise, anti-clockwise, counterclockwise, however way you want to define clockwise. We never really said it. And that's because this theta only defines angles up to sine, right? And that's because there's no good notion of what is a positive or negative angle. Like, if I have an angle, right? I have some angle theta. How do I know that this angle is that way or that way? There's no reference point, right? Like, there's no good way. Which way is it? I don't know. So the angle is really just that kind of, in essence, distance, right? So if you think of like the distance between 2 points, I'm not saying it's the distance from here to here or from there to here. It's just the distance. There's no direction. Same with angle. There's no direction. So you can kind of choose angles to measure them either clockwise or anti-clockwise. And there's no real good reason. This will kind of recover why this is the case in subsection 1.5, which we'll talk about next week when we talk about orientations of vector spaces. But for now, don't worry about it too much. Another thing you might notice is that I said here orthogonal, and I didn't say that the angle is a right angle. And that's because of this kind of note I have here on the side. So in the case of Euclidean vector spaces, these are the same. Orthogonal and perpendicular, aka the angles are 90 degrees, they are equivalent definitions. But orthogonality is itself actually a generalization of perpendicularity to any vector space. In other words, I can use this definition of orthogonal in any vector space, whereas perpendicular, it kind of only works in Euclidean vector spaces. And so this is why we're going to be sticking with this. Because notice how this definition of orthogonal, if I just look at it right here, these don't depend on theta. So it doesn't depend on my angle. It depends on my inner product. And so that's why we didn't define it as a right angle. I just said it's an orthogonal. That's it. Okay, so we'll stop there. I will see you all next week for the continuation of this course. I hope all was good. And as always, if there's questions, let us know so that we can answer them in the review session. I'll see you then live. Have fun. Bye.